having derived the velocity distribution and the pressure distribution, now we will do what we did for plane cuvette flow, that is link all the concepts which you have learnt with this Poiseuille flow, okay, which means that whatever almost all the concepts which we have discussed under linear momentum balance, we started with integral balance, then started deriving the differential balance, discussed about total stress, strain rate, Newton's law of viscosity, and derive the Navier-Stokes equation. Now we are going to connect and link all these with this example. Let us see how do we do that. So now let us start. Now to begin with, we introduced total stress and then viscous stress tensor, and so we introduced the viscous stress tensor, and this is the viscous stress tensor components, and then of course we could express the total stress in terms of hydrostatic stress plus viscous stress, which means it is just adding minus p to the diagonal elements. At this stage we just introduce them as physically meaningful variable, but they were unknowns. Okay. So that is where we introduced these, but in terms of they are just variables. Okay. Now later we discussed about strain rate, okay, and so now we are in a position to evaluate the strain rate. There again, in fact, we first introduced that as a strain rate tensor, but now having derived the parabolic velocity profile, we can evaluate the components of the strain rate tensor. Okay. So this is the velocity profile which we derived, which is quadratic in y, and now we will have to evaluate the components of the strain rate tensor using this velocity distribution. Okay. In this case the Vx depends on y, okay. So all the diagonal components are 0, Vx does not depend on x, it is a fully developed flow profile. So in fact you will have the term dou Vx by dou x only when the flow is developing, okay, or only when the velocity varies, when the velocity varies along the flow direction. Okay. If you have Vx as a function of x, which can happen when the flow is developing along the length of the flow, or remember we had a 2-dimensional flow where there are some inflow or outflow in the y direction, and hence because of that Vx either decreased or increased along the flow direction. There again you can have this normal strain rate component, otherwise there is 0. Okay. And now coming to the off diagonal components of strain rate tensor, of course y is 0, so this term does not contribute, so we will have differentiate Vx with respect to y, which is this term, you have a half there, okay. Okay. And of course when you differentiate you have 2y, 2 cancels out and this is left out, and then you have a half there, okay. And of course Vx is not a function of z, so this is 0, there is no Vz component, so that term is 0, and here Vz is 0, Vy is 0, so that term is also 0. So this component is 0, this component is 0, and it is symmetric, so we can write the off diagonal elements. And in terms of physical significance, so if you look at the components of the strain rate tensor, the diagonal components are 0, and which means that the normal strain rate is 0, and you do have non-zero off diagonal elements, which means that the shear strain rate is not equal to 0. What does it mean? when you say normal strain rate is 0, remember this along the x axis and y axis. So, if you take a line element along the x axis, there is no rate of change of length, and if you take an element along the y axis, there is no rate of change of length. Now, coming to shear strain rate, if you look at the expression for shear strain rate, it depends on dou p by dou x and y. In the top portion of the region where y is greater than 0, which means above the central line, of course dou p by dou x is less than 0. So, in this region, this component, the strain rate tensor component, which is the shear strain rate divided by 2, okay, and that is less than 0, okay, which is negative, and below the central line, of course dou p by dou x is negative, y is also negative, and so the component is greater than 0 or positive, okay, and which means we know that positive shear strain rate means that if you consider two line elements perpendicular to each other at some time t, next some, let us say time t plus delta t, they come towards each other, they approach each other, which means there is a decrease in angle between them. That is what happens below the central line. Above the central line, if you once again consider two line elements at some time t, sometime later t plus delta t, there is a increase in angle between them, okay. So, it becomes, let us say obtuse, and they go away from each other, okay. So, that is how we interpret the components of the strain rate tensor, okay. So, whether they come approach each other or go away from each other depends on whether we consider the two perpendicular line elements above the axis or below the axis. Next we discuss the Newton's law of viscosity to relate viscous stresses and strain rates, okay. Let us do that here as well. That is a relationship between the viscous stress tensor and the strain rate tensor, okay. And in the previous slide we got the expression for strain rate tensor, and multiply by 2 mu will give you the viscous stress tensor, okay. The simple multiplication 2 mu, and we can also find out the total stress tensor adding minus p to the diagonal elements. So, this viscous stress tensor including minus p along the diagonal gives us the total stress tensor, okay. Now, earlier we introduced the viscous stress tensor, total stress tensor as variables. Now, they become known, they were unknown earlier. Now, the velocity profile is known. So, we can evaluate the viscous stress tensor and the total stress tensor, and they become known, okay. And if you notice, there is one difference between the viscous stress tensor for the cuvette flow and this viscous stress tensor for the Poiseuille flow. The difference is that in the earlier case the viscous shear stresses, these were just constants, okay. It was just Vp by h, and Vp was the velocity of the plate, h was the distance between the plate, it was just a constant. But in this case of Poiseuille flow, the viscous stress tensor, the shear stress components, they depend on y, okay. So, they vary linearly with y. In the earlier case it was just a constant, okay. That is what this bullet says, that there is a dependence on y and linear dependence on y, okay. And we have seen this diagram, nice diagram from James O. Wilkes when we discussed pressure distribution, and the shear stress distribution is also shown in this diagram nicely. We will discuss that more about that in detail little later, but just to show that there is a viscous shear stress distribution which varies linearly. We have evaluated the components of the viscous stress tensor. Now we also discussed about stress vector and the relationship between stress vector and stress tensor. So if we know the stress tensor, we can evaluate the stress vector, and also we can evaluate the shear force acting on the plates, and that is what we will do now. Okay. So when I say stress tensor in the present context, it means viscous stress tensor. So let us use the word stress tensor. This is a stress tensor, only the 2 dimensional form is shown here, other terms are 0. Okay. Now when we began solid mechanics, we learned how to evaluate stress vector if we know the stress tensor, and we will use that now. What is the idea? To evaluate the shear force acting on the plates. Okay. Now we have a top plate and a bottom plate, and we will evaluate the shear force acting on the top plate and the bottom plate. Now for the top plate, to evaluate the stress vector, we know the stress vector is given by the dot product between the normal vector and the stress tensor, or matrix multiplication of the normal vector and the stress tensor. What is the normal vector? Normal vector for the top plate is along the positive y direction, and in terms of a vector, in terms of its elements, we represent as 0 and then 1, because the I component is 0 and it is plus j, which means it is plus 1 here, and of course these are the components of the stress tensor. So now if you do a simple matrix multiplication, you will have 0 into 0 and then this 1 into dou p by dou x y, and then the component is along the x direction. So you get a component along the x direction and there is no component along the y direction. Okay. So now this is the stress vector which you obtained using the stress tensor on the normal to the plane. In this case the plane is a top plate. Now then once we found out the stress vector, we found out the normal component and the shear stress component. Okay. I like to distinguish the word component here, we are using in 2 different ways. See, when I use the component here, I mean it is the component of the viscous stress tensor. So what we should recall is this stress element. When I say component here, it is a component of the stress vector. So I should recall this figure. This stress vector was resolved into the normal stress and then 2 shear stresses. In this case, it is because it is 2 dimensional, we will have 1 normal stress and then 1 shear stress. Okay. Of course, the normal stress in this case will turn out to be 0, so you will have only shear stress, but because it is 2 dimensional, we have only the n vector and the S1 vector, and instead of S1 vector I will call it as S vector. Okay. Well, let us proceed. So tau nn represents the normal component of stress vector. Okay. Just to repeat, when I say component here with respect to the stress tensor, component of stress tensor, we should recall this stress element. When we say component here, we are meaning the component of the stress vector, the normal component and the shear stress component. So let us do a dot product. So normal stress is nothing but the projection of stress vector along the normal, which means we have to just take a dot product, and that is what we are doing. Stress vector dotted with n vector, and stress vector just now we have found out dou p by dou x y I, and then 0j, okay, and dotted with the n vector is of course 0I plus 1j. Okay. So, if you take a dot product you will get 0. Of course, even without doing this intuitively we can know that the normal stress component is 0 because the stress vector is along the x direction only, it has component along the x direction only. So, without even doing this we can know that there is no normal stress component of the stress vector. Okay. Now, so there is no viscous normal stress component. Okay. Okay, now let us find out the shear stress component of the stress vector. So, it is a projection of stress vector along the tangential direction, and instead of S1, because we have only one tangential direction, I am taking it as S vector. So, it is Tn dot S vector. Now, what is S vector? The tangential direction, it is along the direction of the plate. So, it is denoted as 1I plus 0j, and stress vector as in the previous step. And if you take the dot product of these two vectors, you get dou p by dou x into y, and we are evaluating at the top plate. So, dou p by dou x into h. So, there is a viscous shear stress component. What is the direction? We have discussed already that dou p by dou x is negative, okay, which means that this will be negative, and so the shear stress is acting along the negative x direction. Why did we say that? H of course a positive number, dou p by dou x is less than 0, and hence tau n s is negative, and hence the shear stress acts along the negative direction. But more importantly, the remember all our discussion on the stresses are all acting on the fluid. So, shear stress component acting on the fluid is along the negative x direction. That also we can easily understand. The plates are fixed, both the plates are fixed, and fluid is moving in this direction. Okay. So, which means that the shear stress on the fluid is along the negative x direction. Okay. So, the fluid tries to, let us say, pull the plate to the right, and the plate tries to pull the fluid to the left. Okay. So, intuitively you can understand that the shear stress component acting on the fluid is along the negative x direction. Okay. So, now let us repeat this for the bottom plate. Okay. So, for the bottom plate, now the n vector is along this direction, we always draw as outward normal, and so n is now 0 minus 1, and of course the same stress tensor. Do a simple matrix multiplication. Now we will get minus dou p by dou x y and I, because once again it has component along the x direction, there is no component along the y direction. Okay. And it is the sign has changed because our normal vector is now 0 minus 1. Why is it 0 minus 1? This is a normal vector pointing along the negative y axis, and so which you represented as minus j vector, that is why it is 0 minus 1. Okay. Of course, do a matrix multiplication with the stress tensor, you get the stress vector. Okay. Now, like we did in the previous case, let us find out the normal component and the shear stress component of the stress vector, and so dot the stress vector, take a dot product of stress vector with the normal vector, and this is the stress vector and this is the normal vector. If you take a dot product, you get a 0. Okay. And as in the last case, we can conclude by looking at the stress vector that there is no normal stress component. Okay. So, no viscous normal stress component. So, let us find out the shear stress component. Okay. Now, the tangential direction is along the positive x axis. This is the stress vector, it is component along the x direction only and no component along the y direction, dotted with the tangential direction, and that vector is along the positive x axis, hence 1 I plus 0 j. Okay. And if you take a dot product of these two vectors, you get minus dou p by dou x y. And now at the bottom plate, remember this is central, that is axis, that is where we have y equal to 0, and so this is the y equal to minus h, and so now if we substitute y equal to minus h, we have dou p by dou x h, which is same as what we obtained in the last case for the top plate, and once again dou p by dou x is negative. So, here again the shear stress component acting on the fluid is along the negative x direction. Of course, that cannot change because through the entire domain fluid flows along the positive x axis. Okay. So, certainly the shear stress acting on the fluid is along the negative x axis. Okay. Now, what we will do is find out the shear force on the plates. Okay. So, let us summarize what we have done in the last two slides. For the top plate, the shear stress component of stress vector, or simply put the shear stress was given by, we found out that it is dou p by dou x h and acts along the negative x direction. Okay. Similarly, for the bottom plate the same expression was obtained, and the shear stress acting on the fluid is along the negative x direction. Now, we will find out the shear force acting on the fluid. Okay. How do you find out? This is the expression for shear stress. We will have to multiply by area. What is area we should multiply? We should multiply by the surface area of the plate, and then twice of that, because we have to account for the top plate and the bottom plate, and that is what we have done here, twice dou p by dou x h into surface area of plate. So, 2 dou p by dou x and of course dou p by dou x into h, and surface area of plate is W into L. Now, to replace in terms of delta p by L, we have seen that dou p by dou x is minus delta p by L, and that replacement has been done here. Now, L cancels out and what we have is minus 2 delta p h W. Remember, this is the total shear force acting on the fluid along the negative x direction. Remember, delta p is positive. Okay. Only dou p by dou x is negative, but delta p is positive, which means that the total shear force on the plates is acting along the positive x direction. Magnitude is 2 delta p h W. Okay. So, what we have done is from the viscous stress tensor found out the stress vector, found out the normal component, it turned out to be 0, found out the shear stress component, and found out what is the shear stress acting on the fluid at the top plate, at the bottom plate, found out the total shear force acting on the fluid, hence found out what is the total shear force acting on the plates. Throughout we work with shear stress, shear force acting on the fluid, because all our discussion right from beginning is with respect to force acting on the fluid. Okay. That is why whenever we discuss about tau etc., it is on the fluid. At the last step we just change the direction and say that the total shear force acting on the plates is negative what we have found out in the previous step. okay. Of course, that is 2 delta p h w. Towards the beginning of linear momentum balance, we derived the integral form of linear momentum balance from Newton's second law of motion by applying Reynolds transport theorem. Okay. We also connect even the integral linear momentum balance to this example. Let us see how do we do that. What is the idea? To once again to evaluate the shear force acting on the plates. Okay. So, let us do that. So, let us write down the integral linear momentum balance. Of course, we are writing for the steady state condition. Left hand side is the net rate of x momentum leaving through the control surface, right hand side we have body forces and surface forces acting along the x direction. Okay. We have inflow at let us say section 1 and outflow at section 2, okay. And so CS is split into CS1 and CS2. Now remember we have assumed, okay, the condition such that we get a fully developed flow. We said Vy is 0, Vz is 0, and from the continuity equation we arrived at the condition that the flow is fully developed, which means that Vx as a function of y does not change with x. This does not happen, okay, which means that whatever velocity profile you have at section 1 is same as the velocity profile what we have at section 2, and for inflow V dot n is negative, for outflow V dot n is positive, and Vx is along the positive x axis, which means that these two terms will cancel each other. Both terms cancel each other. What does it mean? Net rate of momentum leaving the control volume is equal to 0. Whatever rate of momentum enters and same leaves the control volume. Okay. We are writing the linear momentum balance along the x direction and there is no body force along the x direction. Now we will consider Rx as the total shear force exerted by the plates on the fluid flow. Okay. So, whatever these plates exert shear force on the fluid flow is taken as Rx, and we know by physics that it should be along the negative x axis. So, intuitively assumed along the negative x axis. Okay. So, now what happens to the surface force? We have the inlet pressure as P1 and the area as A1. At the exit we have the pressure as P2 and the area as A2. So, we have P1 A1 and then because pressure is compressive it always acts into the control volume. So, we have minus P2 A2, and because we have taken Rx as along the negative x axis, so it is minus Rx. Okay. Like to mention that we have come across a similar example in one of the applications of integral linear momentum balance. So, I would recommend that you can refer those slides as well. The nomenclature has also been almost kept the same. There it was a compressible flow, and there again we are finding out the frictional force. Okay. In this case there we termed it as frictional force. Now we have more formal terminology, namely the total shear force exerted by the plates on the fluid flow. Okay. So, let us put these all together in the integral linear momentum balance. We found out the surface force just now in terms of pressure, area and the shear force. Okay. So, left hand side is 0, right hand side body force is 0. So, this is 0, this is 0, left only with surface forces, and so we substitute on the right hand side, rearrange for Rx. So, P1 A1 minus P2 A2, and of course A1 A2 are both same, though to begin with we said A1 and A2, but what is that A1 or A2? Remember, that is this cross sectional area. So, what is the cross sectional area? 2HW. So, this is delta P. Remember, delta P is in minus out, it is positive. So, P1 minus P2 is delta P. Cross sectional area, as we have discussed now, is 2HW, and this is the same expression which I have obtained earlier also. And what does it represent? Total shear force exerted by the plates on the fluid, and what is the direction? Remember, we have taken Rx along the negative x axis. So, this is the total shear force exerted by the plates on the fluid flow along the negative x axis. And just like we did earlier, what we are interested is the shear force on the plates. So, total shear force exerted by the fluid on the plates is along the positive x direction. Of course, magnitude is 2 delta P HW. Of course, it cannot change. We have found the expression using the integral linear momentum balance. So, now to summarize what we have done in the last few slides, we have gone through one complete cycle of all these topics. Okay. The derivation of Navier-Stokes started with the integral balance. Okay. Then of course, under differential balance we discussed about total stress, strain rate, Newton's law of viscosity, Navier-Stokes equation. Now, we have gone completely almost in the reverse direction. We used the Navier-Stokes equation, solved for the velocity profile, found out strain rate, used Newton's law of viscosity to find out total stress, stress vector, from that the shear force. Okay. And we also use the integral linear momentum balance to find out the total shear force acting on the plates. Okay. Same thing in terms of our the journey slide, we had the integral form of linear momentum balance, okay. And then for the differential balance we discuss about total stress, viscous stress, and then the strain rates, the Newton's law of viscosity, substituted in linear momentum balance the differential form, derive the Navier-Stokes. Now, completely reverse direction now, solve the Navier-Stokes, got the velocity profile, evaluated the strain rate, used Newton's law of viscosity, found out the stress tensor components, found out the stress vector, also found out the shear force acting on the plates, also used the integral form to find out the total shear force acting on the plates. Okay. Of course, once again shown in the form of a cycle, the integral balance, total stress, then strain rate, Newton's law of viscosity, Navier-Stokes, velocity profile. Once the velocity profile is known from the Navier-Stokes, you can find out strain rate, use Newton's law of viscosity, find total stress, stress vector, and then the shear force, which can also be found out from the integral linear momentum balance. So, this example is a very comprehensive example, almost covering right from our beginning of the derivation, from the you can say almost let us say Newton's second law of motion till the Navier-Stokes. Okay. When we came to the forward path, they were all led us to the derivation of Navier-Stokes. Now, we can understand why we really came through that particular path. They were all expressions, dou Vx by dou x, or dou Vy by dou x, or dou Vx by dou y, and then such a combination was strain rate tensor, components of strain rate tensor. But now we can all evaluate them in terms of values as well, in terms of the velocity profile. In terms of measurable values, you can evaluate them.